Hello students, welcome you all back to another session of econometric methods course. In the last few classes, we had been discussing about the simple linear regression model. In the few sessions, we saw the estimators used in the simple linear regression model. We saw the OLS estimators prominently, and we saw how the OLS estimators are derived. Now, in the last class, we saw the properties of OLS estimators. In the last class, we saw the mean of the OLS estimators. The present class, today's class, we are going to see the variance of the OLS estimators, namely alpha hat and beta hat. First, let us derive the variance of beta hat, then we will derive the variance of alpha hat. Let us see that. Suppose beta hat is the OLS estimator of beta. Then we know that beta hat is equal to beta plus sigma wi ui. This particular equation you may refer to the module 9. This implies beta hat minus beta is equal to sigma wi ui. Squaring both sides, we get beta hat minus beta whole square is equal to sigma wi ui whole square. Taking expectations both sides, we get expectation of beta hat minus beta whole square is equal to expectation of sigma wi ui the whole square. In fact, this expectation of beta hat minus beta whole square is nothing but variance of beta hat. So we may write variance of beta hat is equal to expectation of beta hat minus beta whole square is equal to expectation of sigma wi ui the whole square. Expanding the summation square, we may get variance of beta hat is equal to expectation of sigma wi ui square plus 2 into double sigma I not equal to j wi wj ui uj. Now we can take expectations inside this expression wherever there is random variable. Here ui and uj are the random variables. So taking expectations inside, we get sigma wi square expectation of ui square plus 2 into double sigma I not equal to j wi wj expectation of ui uj. Now we are applying the what is assumed in our OLS assumptions. We already know expectation of ui square is equal to sigma square for all I. This is the assumption called homoscedasticity assumption. Again, expectation of ui uj is equal to 0 for all I not equal to j. This is expectation of ui uj is equal to 0. This assumption is called no autocorrelation assumption. So applying this, we get sigma wi square into sigma square, that is no expectation of ui square is sigma square for all I, and expectation of ui uj is equal to 0 for all I not equal to j. So if we reduce this after substituting these values, we get sigma square into wi square. This is equal to sigma square into 1 by sigma xi square. This value we derived from the in our module 9. So therefore, variance of beta hat is equal to sigma square divided by sigma small xi square. Now let us derive the variance of alpha hat. Suppose alpha hat is the OLS estimator of alpha. We know that alpha hat is equal to alpha plus z sigma zi ui, where zi is equal to 1 by n minus wi x bar. Now alpha hat minus alpha is equal to sigma zi ui. Squaring both sides, we get alpha minus alpha whole square is equal to sigma zi ui the whole square. Taking expectations both sides, we get expectation of alpha hat minus alpha whole square is equal to expectation of sigma zi ui the whole square. We already know the expectation of alpha hat minus alpha whole square is the variance of alpha hat, and so variance of alpha hat is equal to expectation of alpha hat minus alpha whole square is equal to expectation of sigma zi ui the whole square. Expanding the summation square, we get variance of alpha hat is equal to expectation of sigma zi ui square plus 2 into double sigma I not equal to j zi zj ui uj. Now we are taking expectations inside. So variance of beta hat is equal to sigma zi square expectation of ui square plus double sigma I not equal to j zi zj expectation of ui uj. Now this may be further simplified. Sigma zi square into sigma square plus double sigma I not equal to j zi zj into 0. This is from the OLS assumptions, because the expectation of ui square is equal to sigma square, a constant for all I, is the homoscedasticity assumption. Similarly, expectation of ui uj I not equal to j is 0 according to no autocorrelation assumption of OLS assumptions. So substituting these values, we get variance of beta hat is equal to sigma zi square sigma square plus 0, that is sigma zi square sigma square. Now we can substitute the value for zi. So we further get variance of beta hat is equal to sigma square into sigma 1 by n minus wi x bar the whole square, since zi is equal to 1 by n minus wi x bar. So we get sigma square sigma 1 by n, actually this is a minus b the whole square like. So the expansion is 1 by n the whole square plus wi x bar the whole square minus 2 into 1 by n into wi x bar. So this may be reduced to 1 by n square plus x bar squares wi square minus 2 x bar can be now clubbed and 1 by n into wi and whole sigma. So this sigma can be taken in. We are taking sigma inside, and we get n into 1 by n square plus x bar square into sigma wi square minus 2x bar by n into wi. Now we already know the values of sigma wi square and sigma wi. We have derived that in the module 9. According to it, sigma wi is equal to 0 and sigma wi square is equal to 1 by sigma xi square. Substitute this value, we get we may cancel the first line, we may cancel these two, and so we get 1 by n plus sigma x bar whole square into, instead of sigma wi square, we may put 1 by sigma xi square plus 2 into x bar by n into 0, because sigma wi is equal to 0. So we may reduce it in the next line, sigma square into 1 by n plus x bar square divided by sigma xi square. So now we may further take an LCM of these two denominators, and we get this expression, right? Actually, this n sigma xi square is taken as the LCM, and so we get sigma xi square plus n x bar whole square. Now we may expand this term, sigma small xi square. We already know small xi is nothing but the deviation from the mean values. So small xi is equal to capital Xi minus x bar. So substituting this, we get sigma small xi square is equal to sigma capital Xi minus x bar the whole square plus this term n x bar the whole square. So now this is like a minus b the whole square, so we can expand this term, that is xi square plus x bar square minus 2 xi x bar. So the whole expression can further be reduced. Now we may take the sigma inside. So now the expression becomes sigma square into sigma xi square, capital Xi square plus n into x bar square minus 2x bar into sigma xi plus n x bar square whole divided by n into sigma small xi square. And now we may substitute value for this term sigma xi. We already know x bar is equal to sigma xi by n. This is the common definition, and from this we may derive sigma xi, sigma capital Xi is equal to n into x bar. We are substituting this value, right? Instead of sigma capital Xi, we substitute n into x bar. So this expression becomes, no other term is changing, only this substitute of value, we get 2 into x bar into n x bar. If we reduce it, we get sigma xi square plus n into x bar square minus 2 n x bar square, 2n x bar square, and this term remains plus n x bar square. So we add these two, and we get plus 2n bar square, and there is already minus 2n x bar square, so both get cancelled. So this three expression get cancelled, and we are left with the only one term, so sigma xi square divided by n into sigma small xi square. Okay, now let us see. Actually, these terms can be rearranged, and we can make it into very plausible terms. First term is sigma square divided by sigma small xi square into sigma capital Xi square divided by n. So with this we know already, this is nothing but variance of beta hat. So this variance of alpha hat is nothing but variance of beta hat into sigma xi capital Xi square divided by n. We already know alpha hat and beta hat are the sample statistic, and so both are random variables, and both are stochastic variables, and so we can find the covariance between alpha hat and beta hat. Now let us see how to derive the covariance between alpha hat and beta hat. The covariance of alpha hat and beta hat nothing but expectation of alpha hat minus alpha into expectation of beta hat minus beta. We know that for the sample regression function, alpha hat is equal to y bar minus beta hat x bar. Also in the population regression function, alpha is equal to y bar minus beta x bar. And if we subtract these two terms, two expressions, we get alpha hat minus alpha is equal to y bar minus beta hat x bar minus y bar minus beta x bar. So taking this minus inside, we get y bar minus beta hat x bar minus y bar plus minus minus plus, so plus beta x bar. So we may get both terms will get cancelled, the y bar terms will get cancelled, and at the end you will have two terms left, and we may reduce these two terms into one, x bar into beta minus beta hat. Substituting this value, now covariance of alpha hat beta hat becomes expectation of beta hat minus beta into x bar beta minus beta hat from the earlier expression. So we substitute this expression for alpha hat minus alpha. So we get these two terms again, x bar can be taken outside because it is a deterministic value, and these are the stochastic values. So expectations can be taken for these stochastic variables. So we get beta hat minus beta into, we can take minus from this expression, so that will become beta minus beta, beta hat minus beta. So if you take minus outside, this expression becomes minus x bar expectation of beta hat minus beta whole square. We already know this is nothing but the variance of beta hat. So covariance of alpha hat and beta hat is nothing but x bar into variance of beta hat, otherwise x bar into sigma square divided by sigma small xi square. Using the characteristics of the stochastic variables alpha hat and beta hat, now we may derive some important properties of the OLS estimators. First and foremost property of OLS estimators are they are all linear. Now we'll prove that alpha hat and beta hat are linear estimators. Now let us take the estimator beta hat. Beta hat is equal to, already we know, sigma small xi small yi divided by sigma small xi square. Now this yi we may expand. We already know this yi is nothing but the deviation value. This small yi is the deviation value, and so we may put small yi as capital yi minus y bar. So this may be written as sigma xi into yi capital yi minus y bar divided by sigma xi square. So we may take this xi inside, and where we get the expression sigma xi capital yi minus y bar into small xi divided by the denominator. And so this expressions can be split. So we may get two expressions. The first expression is this one, and the second expression is this. So we get sigma small xi capital yi divided by sigma xi small xi square minus y bar into sigma small xi divided by sigma xi square small xi square. We already know that this is a deviation value, and we are summing it, and so we get 0. So substituting this value, we get the expression sigma small xi capital yi divided by sigma xi small xi square. So this term will go, and this will remain, and this is the value of beta hat. Now we may write no further rewrite this expression into sigma small wi capital Yi, because we already know small wi is defined as small xi divided by sigma small xi square. So this expression becomes sigma wi capital Yi. From this, we may infer beta hat is a linear function of observations on y. So because of that, we can conclude that beta hat is a linear estimator. The similar expression can be derived for alpha hat as well. Now, immediate property to the linear property is the unbiased property of the OLS estimators. Now let us take for instance the expression of beta hat. Beta hat is already we know is equal to beta plus sigma wi ui. Taking expectations both sides, we may get expectation of beta hat is equal to expectation of beta plus sigma wi ui. So taking expectations inside, because now beta is a scalar value, and if you take the expectations inside, we get beta plus sigma wi expectation of ui. And we already know from the OLS assumption that expectation of ui is equal to 0 for all i's. So we get this term gets 0, and so we get expectation of beta hat is equal to beta. So expectation of beta hat is equal to beta. This is the definition of unbiasedness, and so we may conclude that beta hat is an unbiased estimator of beta. This same kind of derivations can be done for the alpha hat also. So in conclusion, we may say beta hat and alpha hat are unbiased estimators. We have so far seen OLS estimators are linear and unbiased. There is another important property, that in the class of linear unbiased estimators, OLS estimators have got the least variance. This particular property of OLS estimators are called the Gauss-Markov theorem. Let us see how the Gauss-Markov theorem can be proved. So we may say, after the end of this section, OLS estimators are the best linear unbiased estimators, and so having the property of blue, that is best linear unbiased estimator. Now let us see how the this Gauss-Markov theorem can be proved. Let us consider beta star an arbitrary unbiased estimator. We may return this estimator as, because it is a linear estimator, so beta star may be written as sigma ci yi, where ci is some linear weightage, like your beta hat, the OLS estimator. Beta hat is equal to sigma wi yi. Here ci may be taken as wi di, where di is an arbitrary additional term. It may be positive or negative. Now we may derive the properties of ci and di from the properties of beta star. We know beta star is equal to sigma ci capital Yi. This Yi can be substituted. This is a expression we may get from the PRF, population regression function. So we may get this as sigma ci alpha plus beta xi plus ui. We may multiply ci with each of the terms the previous expression. We may get sigma ca alpha plus beta ci xi plus Ci ui. Taking this sigma into the expression, we get alpha into sigma Ci plus beta sigma Ci xi plus sigma Ci ui. We already know that beta star is an arbitrary unbiased estimator. So naturally expectation of beta star is equal to beta 1. Right? To get this expression in the previous identity, this sigma Ci must be 0 and this sigma Ci xi must be equal to 1. Therefore, we get the value sigma Ci is equal to 0 and the value sigma Ci is equal to 1. If this sigma Ci is equal to 0, we may derive the properties of Di. Now we already know Ci is equal to Wi plus Di. So this is equal to sigma Wi plus sigma Di. Both are equal to the sum of it is equal to 0. We already know sigma Wi is equal to 0 and therefore sigma Wi will also be 0. Secondly, sigma Ci capital Xi is equal to 1. This implies we substitute this Ci as Wi plus Di, so it becomes sigma Wix capital Xi plus sigma Di capital Xi. In the module 9, we already know sigma Wi capital Xi is equal to 1. So the sum of the term is equal to 1, and so with this condition it gets 1 plus sigma Di capital Xi is equal to 1. So naturally sigma Di capital Xi is equal to 0. We may derive further values. Sigma Di capital Xi we may substitute that as small xi plus x bar. So we may substitute this identity. We may get sigma Di small xi plus x bar sigma Di. We already know sigma Di as 0, and so the value of this is equal to sigma Di small xi. From the expression sigma Di capital Xi is equal to 0, we get sigma Di small xi is also equal to 0. From this previous derivations, we may also find the value of sigma Wi Di, that is equal to sigma xi Di divided by sigma xi square, because Wi is equal to xi by sigma xi square. So this expression becomes sigma xi Di divided by sigma xi square. We already know sigma xi Di, sigma small xi Di or Di xi is equal to 0, and so this expression, the numerator becomes 0 and the whole entire expression becomes 0. So sigma Wi Di is equal to 0. Now let us derive the variance of beta star. So beta star minus beta is equal to sigma Ci ui from the earlier expression. Squaring both sides, we get the squaring of the summation term sigma Ci ui the whole square. Taking expectations both sides, we get very similar. Actually, the earlier derivations of this kind we have already done. So this is equal to expectation of sigma Ci ui the whole square, expansion of this square of the summation terms, we get sigma Ci ui whole square plus 2 into double sigma I not equal to j Cij ui uj. So this becomes sigma Ci square expectation of ui square plus 2 into double sigma I not equal to j Cij expectation of ui uj. From the OLS assumptions, this becomes from the homoscedasticity assumption, this becomes a constant, and this actually this is 0. So we get finally variance of beta star is equal to sigma ci square sigma square. Now let us see variance of beta star now is equal to sigma ci square sigma square. Sigma square is a constant, so we may take outside. So inside we have sigma ci square. Ci square is is nothing but wi plus di, so we may substitute that expression. So this becomes a plus b the whole square. So this may be written as wi square plus di square plus 2 wi di. We may take the sigma inside, so we get sigma wi square plus sigma di square plus 2 into sigma wi di. So this becomes 0, because since sigma wi di is equal to 0, so we get sigma wi square plus sigma di square. So we get two expressions only. So now if you take the sigma square inside, we get sigma square sigma wi square plus sigma square sigma di square. So this expression may be written as sigma square into 1 by sigma xi square, because sigma wi square we already know nothing but 1 by sigma xi square. So we get two terms, this expression plus another a positive expression. This we know already that this is the variance of beta hat. So what we can conclude is we have variance of beta star equal to the variance of beta plus a positive term. So naturally the variance of beta hat plus some positive expression will make the variance of the arbitrary linear unbiased estimator. So from this we may conclude variance of beta star is greater than variance of beta. Beta star is an arbitrary unbiased estimator. In comparison to the variance of any arbitrary estimator, arbitrary unbiased estimator, variance of OLS estimator is minimum. Hence the Gauss-Markov theorem is proved. From this we may conclude OLS estimator is blue, that is best linear unbiased estimator. The characteristics of the OLS estimators, we have proved the properties of OLS estimators. From the properties we have seen, the OLS estimators are linear, unbiased, and has the least variance. So we may say in conclusion, OLS estimators are easy to calculate, easy to compute. OLS estimators are accurate, and OLS estimators are precise. So the quality and the characteristics of OLS estimators are most wanted, and they can be used for our practical purpose of estimating the parameters in the regression model. In the next classes, we will explain how the OLS estimators are used in the practical sense.